Hey there, welcome to this last lesson in Unit 2C. We are going to talk about semi-log plots, which usually appears on the AP Precalculus exam in the form of one, probably not two, but usually one multiple choice question. So let's go ahead and look at this topic of a semi-log plot. We're learning how to read and interpret a semi-log plot, and you'll be successful if you can interpret the graph of a semi-log plot as well as write the linear equation for a semi-log plot that has this linear pattern. What the heck is a semi-log plot? A semi-log plot is when one of the axes, and it's usually the y-axis, is logarithmically scaled. So the y-axis scale can be a logarithm of any base, but the most common is base 10, our common log, and base e, the natural log. For a base 10 logarithmic scale, a y value of 1 is equal to 10 to the power of 1. And a y value of 2 is equal to 10 to the power of 2, so on and so forth. And you can see an example of a logarithmic scale right here. And logarithmic scales look pretty interesting. You'll notice that the x-axis, your x scale, is exactly the same. 1, 2, 3, 4. Your y-axis is logarithmically scaled, so it will increase. So each line represents 1, so, or I guess here in this case, 0.1, 0.2, 0.3, 0.4, 0.5, 0.6, and then after that we get 2, 3, 4, 5, 6, 7, 8, 9, 10, and then after 10, now each line represents 10, 20, 30, 40, 50, and after 10 to the second, 100, we get 200, 300, 400. So what this ends up doing is the exponential characteristics of an exponential function will appear linear. So data or functions with exponential characteristics will appear linear, or they will linearize is the phrase. So below here we have an exponential function that is 2 to the power of x graphed on a semi-log plot. And so if we went ahead and we graphed this data, right, I could put the number 1 here, put the number 2 here, put the number, 2 to the power of, 2 comma 4 here, and then we have 8. So normally, right, with this proportional increase or proportional rate of change, our function would curve up and look exponential. When we take a logarithmic value of the y-axis, it appears linear, okay? So for an exponential function of the form y equals a times b to the power of x, the linear model for a semi-log plot will be this. We're going to take a log of each side. And so we get y equals log base n, it can be any n, of b to the power of x plus log base n of a, where n must be greater than 0 and cannot be equal to 1. This means that the slope of a line, so if I'm looking at a linear line, y equals mx plus b, and I'll write that right here, y equals mx plus b, our slope is going to be the log of the base, where b is the base of the exponential function, and the y-intercept of the semi-log plot will be log of the a value, okay? So we'll go ahead and look at some examples of that and kind of how that happens. So lastly, slope of a semi-log plot with a linear pattern also indicates a couple things. One, if your straight line is going up, increasing, that is going to be exponential growth, positive slope. Negative slope, right, or a decreasing linear pattern will indicate exponential decay. So let's go ahead and let's check out some of these questions that can appear on the AP Precalculus exam. 1. A semi-log plot is created, which graph provides evidence that f of x is an exponential function. Remember, a semi-log plot will linearize. It'll make an exponential curve look straight. So if we have a semi-log plot, we're looking for a straight or a linear function. That is going to be b. Very easy, nice and easy. Here's a practice problem, and honestly, this is the most common type of question with a semi-log plot that I have seen on practice exams for the AP Precalculus test. They give a table of values for a function g at selected values of x. Which of the following could represent this data in a semi-log plot where the vertical axis is logarithmically scaled? Pause me, try to identify which one is a semi-log plot. Okay. Hopefully you paused, and hopefully you saw the y-axis that is logarithmically scaled, and that's going to be A. The answer here is A. We're increasing here by 500s on B, and we still see an exponential curve. D kind of looks a little bit linear, but aren't we still increasing at constant rates? 10, could be a logarithmically scaled function, but again, our function here appears, linear, okay? And actually, it still appears a little curved. Anyway, so A is the winner there. Okay, now let's go ahead and talk about linearizing an exponential function that is given symbolically or algebraically. A data set that appears exponential is modeled by this function b of x equals 2 times 0.4 to the power of x. The data represented using semi-log plot with a vertical axis logarithmically scaled using a natural logarithm. Which of the following equations could model the linear pattern in a semi-log plot? Well, earlier we talked about the slope of a straight line will be the log of the base. So really that's kind of like your getaway. But I wanted to go ahead and kind of do this. If I take the natural log of 2 times 0.4 to the power of x, isn't that natural log of 2 plus natural log of 0.4 to the power of x? And with the power rule, I can move that x out front. X times the natural log of 0.4. So this just kind of goes to show you when I use my logarithmic properties how that separation occurs. I have log of the a value here plus x times this logarithm of the base. Logarithm of the base. That's going to be your slope. Okay, so we're kind of looking for this natural log of 2 plus natural log of 0.4 times x. A is the answer. Okay, go ahead. I want you to answer this question. A data set that appears exponential is modeled by the function m. M of t is equal to 3 times 4 to the power t. The data represented using a semi-log plot, where the vertical axis is logarithmically scaled with a common logarithm. Which of the following could represent, or could describe the appearance of the data in a semi-log plot? Pause me. Try this example. All right. Hopefully you went ahead and did this one. Really, you want your data to appear linear. If you take a semi-log plot, your data is going to appear linear. So the answer is between these two. Okay, and again, if I take a log here of this function, right? I take log of 3 times 4 to the power of t. This is going to be equal to log of 3 plus log of 4t. 4 to the t power, which gives me t times log of 4. So our slope will be log of the base. Log of the base. Answer here, D. The answer is D. Did you get it? Okay, if not, hopefully you can get this next one. Very similar question here. A set of data appears exponential is graphed using a semi-log plot with the vertical axis logarithmically scaled. If the data is modeled by y equals 3 times 6 to the power of x, which of the following could be the equation of the graph of a semi-log plot? Okay, hopefully you got it. We're looking for this x to be attached to log of 6. X to be attached to log of 6. So I like D. I like D as an answer. So again, here they use different log bases. I know that's going to trip up some of you, but that doesn't really kind of matter. You can take any logarithmic base, right? As long as that base is greater than 0 and it is not 1. Okay. Next practice one. An exponential decay function is represented using a semi-log plot with a vertical axis logarithmically scaled for selected values of x. Which of the following could represent a semi-log plot for this function? Pause me. Try this one. Okay. It's not A or D. B and C are log plots, semi-log plots, but they use a special word here. They say exponential decay, which means decreasing. I want the function that's going down. Answer is B. Okay, hopefully you got that. All right, couple more practice ones here. Which of the following equations could represent exponential decay function when graphed on a semi-log plot with a vertical axis logarithmically scaled? Pause me. Try this one. Okay, they give a logarithmically scaled function, and so it's important to note exponential decay is going to come from a base that is between 0 and 1. So when we're looking at really this portion, right, I'm looking at the slope that's attached to an x, because that's going to be the base. So I'm not going to choose A, because 2, that's bigger than 1. That would be exponential growth. And I'm not going to choose C, because again, 3, that's bigger than 1. So it really comes down to B and D. And D here, this is an exponential function. That's not going to be a semi-log plot. Okay, so answer is going to be B. All right, table of values for an exponential function for selected values of x. Which of the following could be the equation when the function is represented using a semi-log plot with the vertical axis logarithmically scaled? So go ahead, pause me, try this one. And what I recommend doing is I recommend writing this as an exponential function first. That might help you. Okay, here is the exponential function. You have an initial value of 2, and your proportional rate of change is 3, right? 6 divided by 2, 18 divided by 6, 54 divided by 18. Or not 2, did I say 2? It's 3. 6 divided by 2 is 3. So I get 2 times 3 to the power of x. So again, what we're looking for, they use natural logs for all of this, so that's kind of nice. So you would be looking for natural log of 2 plus x times natural log of 3. And I think D. Okay, really too, what you could focus on is just, since this is exponential, you're multiplying by 3 every time, that you know that your slope, right, which is attached to the x, is going to be natural log of 3. Okay, the equation of the graph of a semi-log plot is y equals 2x plus 6, where the x-axis has a standard scale and the y-axis has a logarithmic base 10 scale. Which of the following could be the equation for the exponential function? Well, if my line appears as 2x plus 6, what they're saying here is that the slope is equal to 2. Slope is equal to 2. So, and since this is base 10, right? I want that slope. Remember, it's log base 10 of some value, right? This is going to be your slope, okay? Base 10, this is going to be equal to 2. So what would be that number that would give me 2? And so that's going to be 100, right? So log base 10 of 100 is equal to 2. Okay, so my base is going to be 100 or 2. Okay, and that the only option up here is going to be C. C. So I like C as an answer. Again, because if I took a logarithm, right, of each piece, I would have log of 10 to the power 6 plus x times log of 10 to the power of 2. And because the logarithmic base is base 10, these would cancel. And so that's how we get 6 plus 2x. Okay, so answer is C. That's a weird one. That's a difficult one. Okay, go ahead. Try this next practice one. The equation of the graph of a semi-log plot is y equals 3/5 x plus 1, where the x-axis has a standard scale and the y-axis has a logarithmic base 10. Which of the following could be the equation for the exponential function? Okay, again, very similar. My slope here is 3/5, and so if I'm taking a log base 10 and it's going to give me 3/5, log base 10, that's going to have to be 10 to the power of 3/5 is going to be your base. So answer here, B. Answer is B. We have it also for D, 10 to the 3/5. So I guess I got to talk about this 1. You're going to get 1 when you have log base 10 of 10. So that's going to be your A value. So 10 times 10 to the power of 3/5 to the power of x. Okay, there's your base, there's your A value. All right, hey, that is semi-log plots. What I would take away from this lesson is that semi-log plots make exponential functions look linear. Okay, so B and C here definitely are semi-log plots, and that the scale, right, of the y-axis it goes by tens, then or by ones, then it's going by tens, then it's going by 100s, and then it's going by 1000s, so on and so forth. Okay, so that is a semi-log plot. Hopefully you learned something. Like the video, subscribe. I'll see you next time.